Okay, so today I want to tell you a bit about invariant theory and the kind of recent interest in it, and a bit of it is inspired from problems that came out of complexity. Okay, so here's the plan of my talk. First, I'm going to introduce some of the concepts that we have. Then I'm going to tell you what are the kind of problems we care about, and these problems will be algorithmic in nature, but phrased in a mathematical setting. By mathematical setting, I mean an algebraic setting. And then I'm going to show you some cases where we have good answers, which is what I call positive results, and then some cases where we don't expect to have good answers, and good reasons for why we don't expect to have good answers. Okay. So in this entire talk, K is going to denote an algebraically closed field for me, and unless you have other reasons to care, you can just decide that K is the complex numbers. And G is going to be a reductive group. I don't want to define what a reductive group is, but if you don't know what it is, then you should just keep in mind one of these examples: GLN, SLN, the orthogonal group, the special orthogonal group, finite groups, and tori. Okay, and preferably don't keep in mind finite groups. Preferably keep in mind one of the other more complicated groups. V will denote for me a rational representation, and the word, okay, so there are two words, there are two things in there. One is the word representation and one is the word rational. A representation is a group action which is linear. Okay, so you can think of it as a map from G cross V to V, which when you fix an element of the group will be a linear map from V to V. Okay, or equivalently, you can think of it as a map from G to GLV, which is a group homomorphism. Okay, so group homomorphism. So that's what it means to be a representation. Now, what does the word rational mean? The word rational means that you can look at it in either setting, and it means that these things these maps that I've given are morphisms of varieties. Yeah, so they're given by polynomials in coordinates. Okay, so rational means morphism of varieties. Okay. So morphism of varieties is just a short way of saying if you write these out in coordinates, these maps will be given by polynomials locally. Okay, if it's not familiar enough to you. Now, so the coordinate ring I'm going to denote by K bracket V, which is, you can also think of it as the ring of polynomial functions on V. So if V is an n-dimensional vector space, then this coordinate ring will be a polynomial ring generated by n variables. Yeah, and the n variables will correspond to a set of coordinate functions on V. And then I'm going to define the main object that we're going to think about for this talk, which is going to be the invariant ring. Okay, so this invariant ring is going to be a subring of the coordinate ring, and it's going to consist of all the functions which are invariant. And what does invariant mean? It means it shouldn't be able to detect whether you're taking its value at a point or whether you take the value after applying a group action. Okay, so for all G in G, V in V. Okay, another way of saying this is that this is the same condition as saying that my function f is constant along orbits. Is that clear? So the orbit is, you start from a point V and you see where all you can reach by applying a group action, and your function should take the same value along that whole orbit. Okay, that's what it means to be invariant. Now here's a fact, and perhaps I should okay, just give me a sec. Okay, so let me write it here. So here's a fact. Okay, before that, let me tell you what I mean by, so the orbit is going to have notation which I will just write as G dot V, which is suggestive of itself. So all the points you can get to by applying G. So the orbit closures of 2 points do not intersect if and only if there exists some function which is invariant and takes different values on both of them. one direction is easier, and the direction that's easier is this. So suppose you had a function that took different values in v and w, right? This function takes, let's say this is a and this is b. So it's going to take the value a on the whole orbit of v, therefore it takes the same value on its closure, right? And the same thing here, it takes the value b on its closure. Therefore the closures could not have intersected because the function is taking two different values, right? Now in the other direction is more non-trivial, and it's not going to be always true. This direction is only going to be true because we assume that our group is reductive. Okay? So this is a property that you're able to put an if and only if only because you've chosen your group to be reductive. Okay? So let me not give you the proof of this fact, but let me illustrate, what is the kind of phenomenon that we're capturing here. And let me give it to you in this example where my group is just C star, so it's the one-dimensional torus, and my vector space is the two-dimensional complex vector space. And so if I want to tell you how the group acts on a vector in here, I have to tell you what this applied to x comma y does, and I'm saying it's going to scale the first coordinate by t and scale the second coordinate by t inverse. Okay? What do the orbits look like? Well, I've drawn them out already, and most orbits are going to look like these hyperbolas. So this is a real picture. Yeah, they're all going to look like hyperbolas because whatever you see in this action, you see that the product of the two coordinates is constant, right? No matter what group element you act by. So you're going to get these hyperbolas. They're all going to be orbits, and hyperbolas are closed because they're given by a polynomial equation, right? But then there are going to be three more orbits, which are slightly more interesting. One of them is going to be the x-axis minus 0. So if you look at the orbit of the point 1 comma 0, you'll be able to move it to any other point in the x-axis except the origin. And similarly, y-axis minus 0 is another orbit, and the origin itself is another orbit. Okay. On the other hand, what are the invariant functions? I claim that the only invariant function really is just the product of the two coordinates and any polynomial in it. You could take x squared, y squared, x cubed, y cubed, so on. Okay. And now if you look at this invariant function cannot differentiate between the x-axis minus the origin, the y-axis minus the origin, and the origin itself. It's going to take the value 0 on all three orbits. Okay. And you can take any other invariant function inside here, it won't be able to distinguish them. But it will distinguish every other orbit by just the value that x times y takes on that orbit. Okay. So that's the illustrative example for this fact. Okay. Now I'm going to give you an example of why you might care about orbits and their orbit closures and whether they intersect or not. Okay. And this example is going to be graph isomorphism. Okay. So this is a problem in complexity, but it's an extremely elementary problem, and it asks for this. Given two graphs, delta 1 and delta 2, and let me just fix the vertex set for both. Are they isomorphic? Okay. And I write it as a question, and it can be interpreted in many ways, but I want to interpret this in an algorithmic sense, where the answer to such a question should be an algorithm that says, okay, you give me two graphs, I will tell you it sort of efficiently, hopefully, whether they're the same graph or not up to isomorphism. Okay. Well, the naive algorithm is what? Just permute the vertices using all possible permutations and just check if they're equal, right? But the problem with this is if you want to take all permutations on a vertex set that has size n, that's n factorial, which is a very large number. Okay? And it's even bigger than 2 to the n, which is sort of the standard for what a bad complexity measure is. Okay? So let's see how you can put this in terms of invariant theory. And So I'm going to call AI the adjacency matrix of delta I. So given any graph, you have an adjacency matrix associated with it, where you put a 1 in the ijth spot if there's an edge between I and j. Okay. Now you can write down the adjacency matrices, and if these two graphs are isomorphic, then I claim that the adjacency matrices are related by conjugation by permutation matrix. Okay. You see what permuting the vertices does to an adjacency matrix? It conjugates it by permutation matrix. So I want to say these two graphs are isomorphic if and only if there exists some permutation, and that denotes the symmetric group on n letters, such that m sigma A1 m sigma inverse equals A2, where this denotes the permutation matrix corresponding to sigma. Is that clear? Okay. Now I'm going to put this in the setting of invariant theory. So let's take my group to be the symmetric group and my vector space to be n by n matrices. Right? And why would I do this? Because that's where my adjacency matrices live, right? They're n by n matrices. And now you have the action of this group on this vector space, which is given by precisely that. Sigma acting on A is m sigma A m sigma inverse. This is a group action, right? And now I'm asking, now that question is rephrased to are A1 and A2 in the same orbit? Okay. So graph isomorphism becomes you put in the setting and it becomes a group acting on some vector space, and you're asking, well, are two things in the same orbit? Okay. So, and there's one thing that I want to point out is when you have a finite group acting, the orbits are finite sets which are already closed. So the closure has nothing to do here. So I can apply this fact, and so here is one algorithm. Algorithm is take a set of generators F1 of the invariant ring, and then for each one of them test if they take different values on A1 and A2. Right? And if you could do this entire process efficiently, you would have an algorithm for graph isomorphism. Okay? So the challenge from the perspective of somebody who's purely in algebra is describe a good generating set. Okay? And you want to keep in mind that good means you should be able to also be able to compute it efficiently. Okay?
Are they low degree generators?
Yes, they are low degree generators. Okay, so in this case, I think the degree bound is it should be less than n choose 2 or something. So this is just saying that you can find generators in low degrees. That's not the issue, but there are other issues such as how complicated those polynomials are.
So it's potentially exponentially many monomials.
Yes.
And so
yes.
you need a succinct representation.
Yes. Okay, so with that, I now want to tell you the kind of problems that we are interested in, and each one of these problems you should think of in an algorithmic sense, because in an absolute sense I think some of these problems are just hopeless. We would not be able to solve them as beautifully as we would like. Okay, so this comes to the second part of the talk, which is the problems we care about. So maybe I put this as 2. So the first problem is, of course, a minimal set of generators. And this is a problem that I think goes back to Hilbert, or perhaps even earlier than Hilbert when people were trying it. Maybe they didn't say it in these words. But Hilbert certainly asked you for a way to find the minimal set of generators. Okay, and now when I talk about problems, I'm in this setting. G is a reductive group, V is a rational representation. You're over an algebraically closed field. Okay, and this is sort of a really difficult problem, and we don't really know how to solve this except for a few cases. Okay, now a simpler problem, and which sort of sounds from which you can already see sort of a complexity perspective entering, is the problem of degree bounds. Okay, so the first thing I have to tell you before I tell you this degree bounds is that this ring is a subring of the polynomial ring, but it's also graded. Okay, the polynomial ring has a grading, and this is a graded subring of that. Okay, so degree makes sense, and degree bounds is saying, look, give me a number, give me some number, so that if I look at all the invariants below that degree, they will form a generating set. Okay, they won't be minimal. It won't be a minimal generating set. You might have too many in there, but just some bound which helps me say, oh, you don't have to go larger than this bound. Is that clear? Yeah, just a bound on how large the degree of a set of generators has to be. Okay, now here are two more problems that are a little more that look into the geometry of this action a little more, and the first one is called the null cone problem. So the null cone problem says, given some point in your vector space, you want to decide if 0 is in the orbit closure. Okay, why is it called the null cone problem? Well, this is the set of points such that 0 is in the orbit closure. So this is sort of saying, can you, given some point, can you tell me whether it is in the null cone or not? Okay, this is sort of a special case of the more general problem, which is called orbit closure, in which you're given 2 points and you have to decide if their orbit closures intersect. Okay, and both of these problems are algorithmic in nature. Okay, and then I want to just hint at some more questions, but I don't want to get into the details of these because that will take me forever. And there's a subject called geometric complexity theory, and it's some approach to P versus NP, or rather, VP versus VNP, if you know what that means. And this approach, it's trying to approach this complexity using representation theory and algebraic geometry and these kind of things. And in particular, now it's turned towards invariant theory. And the hope is that one day we will find a result in algebra strong enough to do this. And so let me just hint at what are the kind of conjectures that this has. So the first and sort of the main conjecture it has is called Noether normalization lemma. And this says, this conjectures that there exists a bunch of invariants which are homogeneous. Okay, and with the property that the extension is finite, right? So you look at the subring generated by these, and you look at the invariant ring over this, and that's a finite extension. Well, this, in other words, is just going to mean that the 0 set of these invariants is the null cone. Okay, that requires a little proof, but anyway. But we also want some complexity theory in here, which means that if I have small circuits okay, so it's a problem for another day. Another sort of conjecture that this thing does is it asks for a succinct encoding of generators. That's another conjecture. And I won't tell you what a succinct encoding is, but I will explain it to you in one example. So you will see what kind of things they're looking for. All right? So these are the kind of problems we're interested in. Now I will show you some cases where we can do some of these things, and then some cases where we can't. Okay? So here I come to the third part of my talk, which is positive results. And to begin with, my first example wanted to be something that's about as elementary as I can think of, and yet being somewhat non-trivial. Okay, so the example that I'm going to pick for the first one is going to be, my group is going to be SLN, and my vector space is going to be n by m matrices. So just so that we're clear which one is n and which one is m, the size of the columns is n, and the action is by left multiplication. Okay. Does anybody know what the invariants are in this case? Yes, they're minors. Okay, maximal minors to be precise. So the set of invariants, the ring of invariants, is generated by these guys. So I'm going to call them, I'm going to give them a symbol, be I1 to In, 1 less equal I1 less than I2 less than In less equal m. Well, what does this symbol mean? This symbol means, this means you take, okay, so let me think of these as m vectors, and this is a function that takes the I1th column all the way up to the inth column. So it picks n of these columns and then takes its determinant. Yeah, that's what a maximal minor is. Okay, so that's what the invariants look like. So now that I've put the set of questions up there, do we know a minimal set of generators? And I think we do, is in the sense I've already put it up as a minimal set of generators, right? A priori, you wouldn't know that you could always put it in increasing order, but okay, it's not so hard. What about degree bounds? Well, we know that if these are a minimal set of generators, these are of degree n, right? So degree n invariants suffice, and any smaller degree would not suffice. So we know the degree bounds precisely here. Okay, what about the null cone problem? Okay, how do you decide if 0 is in the closure? Sorry? You would like to, okay, so one way is to evaluate all of these, but how many of these are there? It's m choose n, which could be fairly large, right? Even if m was something like 2n choose n is already very close to 2 to the n. Yeah, so the naivest algorithm would be to just evaluate all of these, and somehow these might be too many. But okay, so but this already tells you, right? So in order for it to be not in the null cone or in the null cone, depends on what the rank of this matrix is, right? So compute the rank. If the rank is full, it's not in the null cone. If the rank is not full, it is in the null cone. Yeah, and computing the rank can be done much faster than checking all of these by just elementary linear algebra. You do this row reduction procedure. Okay, so in this case, the null cone is just to say, okay, take your matrix. If it's full rank, it's not in the null cone. Okay, if and only if. Okay. So, well, in some sense, I got away without using invariant theory here, in some vague sense, because I did not use the invariance as my test. But what about orbit closure? Okay, and if you get bored, you might try to do this during the talk. Okay, so given two different matrices, how do you decide whether the orbit closures intersect or not? When you know that the set of invariants you have to use is too many. So you have to find some way to cut down the set of invariants or some other argument that works for you. Okay, so I will leave that for now. But let me give you this what the succinct encoding of generators is, right? So as we figured out, there are too many of them, which apparently is not so good for algorithms. So we want a way to pack them all together, and I'm going to describe for you something, and hopefully you understand roughly what something like this means. Okay, so I'm going to take these extra variables called xij's, and I'm going to create an n by n matrix. The first row of that n by n matrix is going to look like x11 v1 plus x12 v2 plus x1m vm. Okay, so I take a formal linear combination of these columns. Is that clear? Where these xij's are just some variables. My second column is also going to be like this: x21 v1 plus x2m vm. And I do this, how many? I make n columns out of here. So my last column is going to look like this: xn m vm. And now I take its determinant. Okay. So if I take the determinant of such a matrix, I claim that this determinant, when you expand it out, will be a sum of, let me write this down, p I1 to in and x1 I1, x2 I2, xn in. Okay. So I want you to think about what is the coefficient of x1 I1 times x2 I2 times xn in when you expand this determinant out, and the claim is it's going to be exactly this. Okay. So in that sense, I have packed all these invariants in one expression. We're using some extra variables, and that's what a succinct encoding means. And what is the succinct part of this means is just you just need to know one thing. One is I can write all of these down pretty easily. It's just multiplying and adding, not too much. And there are small circuits for the determinant. That's the one other thing you need to know. Okay? And perhaps this is one thing that you should know, independent of how much computational complexity you're associated with, is that determinants are easy to compute. Yeah, that's the least you should take away from this talk. And so every time you can write a determinantal formula and the things inside are not so bad, that's good from a complexity theory sense. Yeah. So that's roughly all I'm going to tell you about succinct encoding. So this is sort of a very, very simple example, and so now I get to some more complicated examples, and at some point I will tell you what these examples also have to do with complexity. Okay, so here are two examples, and I will explain this to you slowly. So the first example is going to be okay. So there was already the first example. So this is the second example. It's called matrix invariants. And this was studied way back in the 60s and the 70s already, and there was reason to study them from the point of view of polynomial identities and so on. And here the group is GLN, and it's acting on m tuples of n by n matrices. And the way it acts is it conjugates every matrix. So it takes an m tuple of matrices, and given a group element, the way it acts is it conjugates each matrix. Is that clear? Okay. Now, okay, so let me just tell you some invariants and let's see if we agree. If I take the trace of x1, is this an invariant function? This is an invariant function because if you conjugate a matrix, the trace doesn't change. Correct? What about the determinant? The determinant also doesn't change, right? Now there are a bunch of things in between the trace and the determinant that you get if you look at the characteristic polynomial. Right? If you look at the characteristic polynomial of a matrix, which I've written down here as the determinant of identity plus t times x. Yeah, there's usually a minus there, but I'm going to ignore that for now. You expand it out, and the coefficient of t to the j is going to be what I call the jth characteristic coefficient. Yeah, I have to call it something. And all of those are also going to be invariant. Okay, and I'm just pointing out that the first characteristic coefficient is the trace and the last one is the determinant. Okay. Now, not just in one matrix, you can take any monomial in the matrices, and then you can take its trace, or you can take its determinant, or you can take one of these other characteristic coefficients, and they will all be invariants. Okay, and this is a theorem of Procesi or Sibirsky in characteristic 0, and in positive characteristic it's due to Duncan. that these are all the invariants, in the sense that these form a generating set. But you see, I mean, the way it's been written, the set of generators is infinite at the moment. And there is no bound, because I did not tell you you must take monomials of a certain size. I did not tell you what the coefficients are, so on. Okay? So let's see where we are regarding that story.
These coordinates don't interact with each other at all. It seems like
What do you mean?
these x1, x2, xm, they don't interact with each other.
Well, when you multiply them.
Alright, no, but in the representation itself, isn't that?
Oh, in the representation itself? Yes, they don't coordinate. So there is a representation where on n by n matrices, and I'm taking m copies of that representation.
And it became much.
It becomes more tricky.
Sorry.
Yeah.
Why is this infinite generators? Don't you have a finite matrix size matrices?
Yes?
I'm taking the limit as in.
No. But how large can a monomial? Can you tell me a priori how big a monomial I should stop at?
I see.
Yeah. I mean, so a monomial of degree r means this is going to be a matrix that's filled with degree r polynomials, and so you take its trace, that would be degree r.
I see.
And this r could, at the moment, just be anything until you give me an argument for why it shouldn't be something larger than. Right?
So even for m equal 1, you're just taking powers of the same.
Yes. But for m equals 1, you should be able to tell me that that at some point it's enough. Yeah, it's. I mean, it need not strike you immediately, but the point is, it has something to do with. So if you have just one matrix and you take powers and traces and whatever, this becomes a symmetric function in the eigenvalues, right? And then Newton's theorem, or I don't remember whoever, will tell you that the elementary symmetric functions from a generating set. And there are n eigenvalues, so you just have to look at the first n elementary symmetric functions. Yeah.
And for 2, this is completely breaks down.
For 2, the argument completely breaks down. Yes. Because now you have to take these so the other thing I have to point out is that these monomials are not commutative monomials, right? They're non-commutative monomials because you're multiplying matrices. So you could do x1, x2, x1, x2, x1, x2, and so on. You can keep doing this. Okay. So a minimal set of generators, as I said, is perhaps a hopeless question in this case. So let me tell you what the results that we know currently on this setup is. In characteristic 0, the degree bound is n squared, and this is due to Rasmus law, where the point in characteristic 0 is that you don't really have to take these higher characteristic coefficients. You can just write them as traces of some powers. And you won't be able to do this in positive characteristic due to some divisibility issues. Okay? And so what Rasmus law was doing was completely independent of them. He was just studying identities between traces of monomials. Some completely different reason. And he simply showed that if you take the trace of some if he simply showed this. He said, look, if you take trace of x1 to xn squared plus 1, he can write this as sums of products of smaller traces. Okay? He just showed this. And once you have this, and you look at that, you will be able to conclude that you only need invariants of up to degree n squared. Okay? And the key thing about n squared is that it's polynomial, as opposed to exponential, or something even larger. Okay? But this was a characteristic 0 argument. And an arbitrary characteristic, for a long time, nothing close to this was known. And recently, my advisor Harm Dirksen and myself, we proved an upper bound of m plus 1 n to the 4. Okay, and there's also one thing that you probably will notice eventually is that in you're able to get bounds that have nothing to do with m. Okay, this is in some sense a consequence of the representation theory of GLM being semi-simple in characteristic 0. Okay. But in a way that's not obvious at all. Okay, it requires proof, and it's a theorem of Weil that you can do this. Okay. An interesting corollary of this is the following statement, and this is due to Domokos. It's extremely elementary and sort of surprising that you might need to come about in this roundabout way. And it says the following. Suppose A is an associative algebra. I'm not assuming commutativity. Okay? And it's generated by m elements. So let's say it's generated by A1 up to Am. Okay? M elements. And suppose that every element in A, when you take to the power n, is equal to 0. Okay? If you have this assumption, then the claim is that no matter what monomial you take of length m plus 2 n to the 4, you will always get 0. Okay? This number, this is called the Nagata. This is an upper bound. So let's see. Nagata posed the problem of saying what is the best number you can put here. Yeah, and Higman had an answer that began with 2 to the n, improved by Rasmussen and characteristic 0, and that was all completely straightforward. Straightforward in the sense that you search for exactly this, right? But now, for some reason, positive characteristic, you're able to get an answer to this that's not direct, but through some other bound in invariant theory. Okay, but this is a fairly straightforward question for you to think about and see how you can get an answer to this. Okay, elementary.
And the dependence on m is needed.
Absolutely.
And a non-linear growth in n is also needed.
It's unclear. Yeah. Okay, so let me also tell you something about the more algorithmic problems, the orbit closure problem. And in characteristic 0, there was an algorithm given by Forbes and Spilka, which was based upon ROABPs. These are called read-once algebraic branching programs. And for some reason, there's a good algorithm to do this, and they were able to put this in the setting, and they were able to get a good algorithm there. Okay? And this fails in arbitrary characteristic, but we still give an algorithm that does this in polynomial time. And the only reason I'm telling you this is because there's a certain implication of this algorithm. The algorithm implies that invariants of degree less equal n root n and 2n root n. Okay, so n root n is in characteristic 0, 2n root n is an arbitrary characteristic, suffice to separate orbit closures. Okay. So if you remember in the graph isomorphism problem, I said, look, you test all the generators. Okay. But there's no reason that you actually need all the generators if all you want to do is to separate orbit closures, right? You might get away with a subset of generators. Yeah? And in this case, we have degree bounds that are m plus 1 n to the 4, or in characteristic 0 even n squared. And here's a non-trivial statement that says, look, you only have to go to n to the 3 over 2. If you just look at invariance up to that degree, you will already separate orbit closures. And the really cool part about it is that this result comes out of analyzing an algorithm, something that previously was not known. And I still don't know how to do it, how to get this number in any other way. Okay.
Do you ever care about how many you need?
Yes, we absolutely care about it, but we can't solve that problem yet. And I think that is sort of related to that conjecture. Okay, so that's with this case of matrix invariance. And let me tell you the case of matrix semi-invariance, and I'll be very quick. Okay, let me see what I want to do. I will erase this. I gave you all, I gave you one easy example and one non-trivial example that we had to work hard, but I didn't show any of the proofs. But how did I enter into this subject? Is it came through this guy, and there's a very small tweak here. Instead of GLN acting on empty pools of matrices, I have SLN cross SLN acting on them. And the way they act is one multiplies on the left, the other multiplies on the right, with an inverse to make sure it's an action. Okay, and in this case, the invariants have a determinantal description. But here's why this is important. This question is important for the following problem. So here's a question I present to you. If I give you an expression like this, AB inverse A plus. Okay, so I write down an expression like this, and I ask you the question: is this side equal to this side using only formal rules of associativity, multiplication, inverse, and so on? Okay, so I'm not even imposing commutativity. Is this an identity? Is this a God-given identity or not? Okay, yeah.
Just to make sure, so the question is, does that relation hold in every division algebra?
That's one way of putting it. Yeah. So one way of putting it is, does this hold in every division algebra?
And it must be because you looked at your paper to write it down.
Yes, absolutely. And you can sit and work it out. This is maybe doable in about 10 minutes of work. You'll spot exactly what to do. Now, if I give you something that's about 100 lines long, how do you check this? Okay. So let's do this first in the commutative world, right? So if I give you some polynomial identity, I gave you some polynomial on the left and some polynomial on the right, and I asked, are they equal? How would you check this? Okay, let's forget complexity, just naively. How would you check this? Expand it all out and check each monomial. Yeah, expand it all out and check that the coefficients of each monomial match. How would you do it in this case? And the thing that I really want to point to you is you have what's called a nested inverse. How do you get rid of that? You have to somehow simplify this, right? You have to somehow try and simplify it until you get to something that you can say yes or no to. How do you get rid of a nested inverse? Okay, in this case, you will see how to get rid of it if you try hard enough. But I give you something reasonably long, and how would you ever guess at this? Okay, and the point is that the null cone. Okay, so an algorithm for null cone for matrix semi-invariants in some funny way will imply an algorithm for, and this is in the non-commutative world, so I will call it non-commutative, rational identity testing. Okay, so this requires a bit of work that I won't at the moment tell you about, but for some reason the null cone problem in this case captures this problem of non-commutative rational identity testing, which you think is for which at the moment we don't even have a naive algorithm. As we just discussed, we don't have a naive algorithm. I give you a big expression, you don't know what to do, you don't know where to start, you don't know where to end. Okay, so let me tell you the state of art here. So degree bounds is mn to the 4, and this is due to Dirksen and myself. An algorithm for the null cone came in there were two algorithms given for the null cone. One was by Ivanios, Kyaw, and Subramaniam, and this was algebraic, and it depends on the bounds, right? So it requires the bounds. And then there's another algorithm which is due to Garg, Gurwitz, Oliveira, and Vigdison, which is analytic. In some really strange way, this corresponds to this problem of operator scaling. And these guys solve this problem. Again, when I say solve this problem, algorithmically solve this problem. And both of these will give me algorithms for the null cone in this case, which become algorithms for this problem of non-commutative rational identity testing. Okay? This is in every characteristic with some assumptions on field size, whatever. Okay. And similarly, the orbit closure in this case, again, we have an algebraic algorithm due to Dirksen and myself. And there's an analytic algorithm which extends these ideas. Again, this is again stuck in characteristic 0, where this works in any characteristic. And the point is, both of these algorithms now, for some reason, require degree bounds. Okay? For the null cone, they did not require degree bounds, but for the orbit closure, both algorithms require degree bounds. So what I want to say is that this problem of degree bounds is maybe not, we don't understand exactly how it's connected to all these algorithms, but it just so happens that whenever you have good degree bounds, you just happen to get good algorithms. Okay, so that's the punchline. There we go.
Before you leave this, I asked a question about this one.
Sure.
Why are these called semi-invariants?
Yes, this is this terminology comes from quivers. So let me give this to you quickly.
If it's off topic, you don't have to.
No, it's not too far. So a quiver is something where you have a bunch of vertices and arrows. If you have one vertex and a bunch of arrows, and the representation of it is you put a vector space here and a matrix for each arrow. So that's M matrices, and the symmetry action is the general linear group of this vertex. That's how matrix invariance acts. Okay, so that was the matrix invariance. But if you want matrix semi-invariance, you take this quiver. Yeah, you put a vector space n dimensional here, n matrices. Now you have a GLN and a GLN acting on both sides. But if you try to take invariance with respect to GLN cross GLN, you will get nothing. And so you take invariance with respect to SLN cross SLN, and that's why it's a semi-invariant rather than an invariant.
Oh, I see.
Yeah. So
So then are you saying like for every quiver you could do this, or is it?
for every quiver you could do this, but the point is when you try to do it for other quivers, you will add some more weights and so on, which in this case just happens to be one weight that works. So it just yeah. So you see the word semi even more when you try to take a bigger quiver, and then you see what the thing is. I did not give it that name. Okay, what shall we do now? All right. So with that I conclude positive results. Now I'm going to tell you some negative results. Yeah. Yeah.
Maybe a little bit off topic.
Sure.
What if I change you the field and give you some finite field?
Yes.
How much of this remains?
A lot of it will be troublesome, and there are all kinds of issues there. For one, if you take a finite field, all orbits are closed.
Okay.
Right? All orbits are closed. So I'm not sure this statement will hold anymore. Yeah, so you have to wonder what exactly you want. You might ask for orbit closure after going to the algebraic closure or something, but then you're back to being with an algebraic closed field. So there are certainly questions that are interesting from the finite field perspective. It does not fit as nicely. You go to a different level and it has a different flavor. Okay. So maybe 10 minutes. Okay, so number 4, negative results. Okay, so the first negative result is one of bad degree bounds. I'm going to give you a natural example from natural in the sense of the natural extension of the cases we've been discussing, in which you just have the degree bounds are just not good, and so you have to find some way to do it. The point was that, as I showed you in the matrix semi-invariant case, there were these analytic algorithms, right? So an analytic algorithm can run independent of whether you understand your invariant ring or not, and somehow the analysis requires a good understanding of your invariant ring. Okay? So these analytic algorithms will also exist in this case. For example, if you take SL, for later convenience I'm going to put 3n, but don't mind that. 3n plus SL 3n acting on k to the 3n tensor k to the 3n m copies. Okay? This I claim is a natural generalization of matrices, because matrices are two tensors. yeah, and you had an SLN cross SLN acting on it. Okay, so this is a natural generalization, and the analytic algorithm just goes through. It's just not clear how quickly it converges, and so the question is, if you had good degree bounds, maybe it converges quickly. And here's a sort of a no-go result, is that invariants of degree less equal 2 over 3 4 to the n minus 1 do not generate. Yeah, and again, this is a result of mine with my advisor Hans Bergson. Okay. Now, how do you prove such a result? How do you prove invariants of a certain degree just don't suffice? And this number is not even small, even if you put in n equal to 2 or 3. It's already pretty large. So the idea is that here's the idea. Suppose, okay, and we will, I won't put it precisely here, but I will just give you a flavor of the idea. You can have a surjection of invariant rings if you have the following things. If you have a point in here with a closed orbit and the stabilizer is equal to h. Okay, so there's something called Grosjean's principle, and you work this around a little bit, and you get the following kind of surjection. Okay, the surjection requires two conditions. It requires you to be able to find some point with a closed orbit, and it requires you to be able to compute its stabilizer. And so what this allows you to do is it takes one invariant ring and surjects it onto a different invariant ring. Now, what's the key? I mean, okay, it looks like I've taken one problem and reduced it to another problem. Both look like invariant rings. The point is, if you can choose your point carefully, you can make your stabilizer what you want. Yeah, assuming it's possible, right? So if this stabilizer is a torus, then this side becomes easier. For torus actions, it's much easier to understand what the invariant rings are. It becomes a problem in linear algebra or convex polytopes or something like this. Okay, and if you're good enough, I mean, if you can find a point that's good enough, you can make this side of it trivial. And okay, the point about surjections is, if this could not be generated by a certain degree, then this also cannot. Yeah, because any set of generators will surject onto a set of generators. Okay, so that's kind of the idea there. And so this is why, I meant to give you that explanation for this particular point. This result is in characteristic 0 only at the moment. And the reason we're stuck is because we don't know how to show this in positive characteristic. Okay, so that's the first question to the audience, first of many. How can you show that the orbit of any point is closed in positive characteristic? Okay, that's something, if you have any ideas on, you can help me with. Okay, and my second bad result is NP hardness of generators. Okay. Now it's going to be funny. I'm going to keep adding number of tensor factors, SLN, and it's going to act on let me say kn, tensor kn, tensor kn, tensor kn. Each factor acts on its corresponding tensor factor. Okay, so let me call this G, let me call this V. Now I'm going to make a bunch of claims. So the first claim is that homogeneous invariant must have degrees that are multiples of n. Okay, this is just a consequence of the nth root of unity being inside SLN. That's the first claim. Okay, the second claim is degree n invariants are one dimensional. So in some sense, whatever this degree n invariant is, it's essential. Yeah, it's the lowest degree, and it's going to be essential in any set of generators that you have. Any set of generators that you have, one of them will have to have a degree n component, and that degree n component will have to be this guy. In that sense, it's essential. Okay, so essential. And this guy is an alternating sum of 4D matchings. Okay, so you take a 4D matching M, and you take its sign, and I will explain these terms to you. Okay, and this guy is called the Pascal determinant. I only learnt of this recently, so I do not know what exactly this has to do with some other branch of math. And the point is that this is VNP hard. Okay, now if you don't know what VNP hard is, forget about it. Just know that it's hard to compute. And let me tell you something else that will convince you that it's a hard to compute invariant. And so to do this, I have to tell you what these 4D matchings are. I mean, I wrote down something, but I have to tell you what this thing is, because what is a 4D matching and what does these symbols mean? Okay? So 4D matching is something that looks like this. So you take 4 sets of vertices, and a matching. Okay, so a hyperedge is something that looks like this. Okay, that's what a hyperedge is. It takes one vertex from each thing. And so to such an edge, I will associate a coordinate 1, 2, 2, 1. So if you look at this, it's a 4 tensor product, right? So coordinates in that are naturally indexed by 4 numbers. It's a 4-dimensional matrix. Okay, so every hyperedge in here gives you one such coordinate there. And a matching means you take a bunch of such hyperedges, which take each vertex precisely once. Okay, so to do this, you need n hyperedges. And so when I say x to the m, I mean you take a product of those guys, which are all inside this matching. Yeah, so you take a matching, you took this guy, maybe you took this guy, and let's say we just had 3. And if you took that matching, I would have one edge corresponds to that, the other edge corresponds to 2, 1, 1, 2, and this guy corresponds to x, 3, 3, 3. So this guy here would be x, 1, 2, 2, 1, x, 2, 1, 1, 2, x, 3, 3, 3, 3. That would be x to the m. Correct? And then there's a sign associated with it, which is not too hard to understand, is any such matching will give me a matching between these 2 guys in particular. Right? And a matching between these 2 guys and a matching between those 2 guys. But a matching between any 2 things is a permutation. And you take the product of the signs of permutations of this matching, and that matching. Okay? So there is some way to get a sign. You stick the sign anyway. But the point is that if I get, so this problem of 4D matchings is NP hard. Okay? So 4D matchings is NP hard. What does this mean? This means if somebody gave you a subset of the edges, somebody gave you a bunch of hyperedges, and they said, is there a matching among these edges? To be able to detect this is NP hard. And this is the source of this guy being VNP hard. Okay, so if you could compute that easily, you'd have a polynomial time algorithm for this, and P would be equal to NP, and our life would be much simpler. Okay, so with that, I'm going to end.